Imagine you're on your favorite ride, but something doesn't seem quite right. As you ascend the lift hill, you realize when you get to the top that your restraint's not locked. In this day and age, we have become dependent on advanced safety systems in rides to keep us safe from harm. These systems control motors, tell brakes when to open and close, and do things like preventing trains from colliding while they're out on the track. But there's another critical part to ride operation that, to this day, the safety system doesn't know. And it's a flaw that can kill the unsuspecting rider in the worst case scenario. What if I told you rides can't tell if your restraint is locked? Let's find out why.
Now get ready. Here we go.
Ladies and gentlemen, welcome to the Ryan the Ride Mechanic channel. Thank you for coming back today. This is where coaster nerds come to learn more and the general public comes to get overwhelmed with ride knowledge. In 1907, Christopher Voigt and Welcome Mosley developed and built the Coney Island roller coaster Drop the Dip. This coaster was the first to introduce lap bars due to its groundbreaking aggressive design. Since then, the amusement industry has been constantly working to improve the design and improve the safety of the control systems in rides. With the introduction of logic controllers for ride safety systems, manufacturers have been working to close the gaps and eliminate human error out of the safety equation. Even with the implementation of advanced logic control systems, rides still can't monitor certain aspects of the safety critical operations, like determining if your restraint's locked. In fact, the restraint that holds you in the ride is not verified locked by the control system at all. How can that be possible? When it comes to restraints on rides, the truth is restraints are actually not verified to be locked by the control system at all, but they are just assumed locked. Now, I know in the comments below I have operations from all parks firing up their rebuttals. They will say, when we press the lock button, the seat light goes from red to green. Now, this is a correct statement. However, the ride is assuming that the seats are in fact locked. Now, here's how the ride assumes that the restraints are locked. When the ride is told to unlock the restraints, it takes actions. For the purpose of this example, I'll use a roller coaster with mechanical restraints. The unlock command is given. Under the train, a pneumatic valve, known as an enabling valve, opens and allows air pressure to the unlock valves. The ride knows this happened because when it energized the enable valve relay, the open contact of the relay closed, showing the mechanical change of state on the relay. At the same time, a pressure switch attached to the air line changed state from closed to open. This shows that the mechanical valve let pressure in the line to feed the unlock platens. Now the ride commands the 4 platens, controlling 2 rows each, typically, to unlock. The unlock platen valves energize. The ride knows this happened because when it energized the unlock platen valve relay, the open contact of the relay closed, showing the mechanical change of state on the relay. But this time, there's no pressure switch in the line. This time, the ride knows the valve changed state because the proximity sensors that monitor the platen in the down position both turned off. The loss of signal through these sensors has confirmed that the unlock platens have raised and connected with the train. At this point, the restraints are now assumed to be unlocked. Let's talk a little bit about the restraints assumed to be unlocked. Well, the manufacturer looked at the scenarios of the restraints not unlocking and said, well, what's the worst case? Well, the restraints don't open. Well, if they don't open, how will the operators know? Because the people won't get out of the seats. Then operations can determine if there's a minor issue that they can correct, or if something is more damaged and maintenance is required. Now our new group of passengers come onto the train, and they're eager to ride. As the guests take their seat on the ride, the operator commands the restraints to lock. When the restraint lock button is pressed, the enable platen valves are shut off. The ride controller knows they were shut off because both relays change state and are giving the correct input showing they are off now. The pressure switch in the unlock airline has gone low, showing no more pressure left in the airline. The platen actuator proximity sensors have gone high, showing the platen has retracted to its closed or down position. When all 5 of these devices align in the logic, The panel at the main operator control console now indicates green locked. But the restraints are wide open. Several seats are empty. How does it know the restraints are locked? Well, it doesn't. The ride has assumed that the restraints are now locked. Engineers working with probability equations have determined that there is a very high likelihood that the restraint is locked, but there is also a small percentage that the restraint has failed and it is still unlocked. The failures in these scenarios are more than likely due to mechanical bind, such as a failed push-pull cable or a lack of grease in the assembly. So we'll ask the same question we did before. What happens if they don't lock? The manufacturer looks at the scenario of the restraints not locking. What's the worst case? Well, the restraints don't lock. How will the operators know? They won't, unless someone points it out to them. So they will require guests to push up on the restraint and verify it's locked. Well, what happens if the guests don't do that? Well, we'll have an operator come by each seat and pull up on the restraint and verify it's locked before dispatch. Now that the assumption of the restraints being locked, backed with a physical check that they are in fact closed, is enough to ensure the restraints are safely locked. The computer has now told its mechanical equipment to stop trying to unlock the ride, and it did. Now the operators come by and verified that the restraints cannot open anymore. This is how the green indicator on the ride's control panel is now assuming that the restraint is locked. Have you seen some models where you pull your restraints down and the green light illuminates on the side? These green lights are actually monitoring a secondary safety system. These secondary safety systems engage once the restraint has been pulled down far enough. With these systems, the primary latches cannot be monitored because they do not know how big of a person they're supposed to be holding in. By adding more proximity sensors, trying to monitor the primary, the system can no longer be small and compact, and it now becomes very large. The system also requires an extraordinary amount of maintenance and adjustment to keep all the sensors working properly. This means downtime goes through the roof, and parks won't want that. Even if you've added hundreds more sensors to each aspect of the restraint, safety committees and insurance companies will still want the restraint to be checked to ensure that it's locked. Now, there are more advanced rides out there that have much more monitoring capabilities. Even these rides cannot determine if the primary locking mechanism is in fact locked. When we talk more about current rides, most of them are using hydraulic cylinders. The trains use onboard PLCs to monitor the seats and other various components of the train. PLC stands for Programmable Logic Controller. So let's talk about some common misconceptions. Onboard programmable logic controllers have started recently popping up inside of roller coaster trains. I hear it all the time. People say that the PLC is constantly monitoring the seats, and if there's ever a problem, the ride will just shut down. This is actually a false statement for the coasters. Onboard PLCs can only monitor the train's restraints while the train is sitting in the home position. Once the train has left the station, the ride no longer knows the status of those restraints. It is possible to broadcast this information from around the track back to the PLC. However, out on the run track, there is nothing the ride can do if suddenly something is monitored to be open. The ride can e-stop, but won't stop the train until it enters the next braking zone. Also, trains have no batteries in them to power these units either. They get their power from a bus rail only located in the station area. A bus rail is a brass conductor that runs alongside the train that allows electricity to be picked up onto the train by a little unit called a brush that runs alongside the train with it. Where this scenario is more correct is on a dark ride. Since dark rides require power to move along the track, they can do extra things like add rails to conduct things like information such as whether the restraints are locked or unlocked or other vitals of the train/car. Even with dark rides, we assume locked means that the seatbelt has been checked. Unlocked means the tongue of the seatbelt is no longer inserted into the buckle. Back to roller coasters. The majority of roller coasters these days use hydraulic cylinders to hold the restraints down. The concept of the hydraulic cylinder is very simple. Hydraulic cylinders are only allowed to move one way, and then we apply a small amount of electrical current to the valve internal inside the body, and then the hydraulic cylinder is allowed to go the opposite way, i.e. open. So even with hydraulic cylinders, the same assumption is made. Well, if we don't give it power, then it's locked by default. But we know this logic is flawed because we have demonstrated that these cylinders can fail sometimes midday on the ride. So how do we avoid this problem? Well, we can add a second cylinder to the restraint. Now, where one fails, the other one should take its place. Even then, we're still assuming that they're both locked. So even with these high-tech cylinders, we still have the operators come by and tug on that restraint to make sure it's all the way down and is in fact locked. The majority of the monitoring that happens on the train's restraints is actually to monitor whether the restraint is far enough down or not. Most flat rides also do the same thing. This logic can't be relied on 100% as the minimum restraint angle that those sensors are monitoring doesn't necessarily mean that the restraint is down all the way. For example, I'm a big person, so when I get on some of these rides, I struggle to make the minimum restraint angle on some of them. When I would ride these same rides with my son when he was 5 years old, he was half the thickness I was. So where my minimum restraint angle struggled to make, his had plenty of room to spare. So the minimum restraint angle that the ride is monitoring actually has nothing to do with him fitting in the ride safely. The minimum restraint angle is actually only used to verify that the restraint is down far enough for larger guests not to come out of the ride. This is the reason why when most operators come by, they're instructed to push down on the restraint first, is to ensure that there's no gap underneath the passenger and the restraint. And then once they verify that there's no gap, they're supposed to pull up to make sure that the restraint is in fact locked. Some parks mix the responsibility. The operators will come by and they'll ask you to pull up and push down on your restraint as they walk by. As they ask you for this, they are actually watching you at the same time to verify that the restraints have no excessive play in either direction, indicating to them that they are in fact locked and down all the way. Disney actually does a great job of this. On a ride like Disney Star Tours, the cast members go down and ask for each restraint buckle to be checked one at a time, asking you to pull on the yellow tab. This entire time they're watching everybody do this to verify that they are in fact locked. They do this because there's not enough time between cycles, nor is there enough room for cast members to walk safely down each individual aisle and tug on every single person's seatbelt. They can't do that. So they ask for it to be done visually so they can see it. Some of the star flyers out there use these very expensive seatbelt latches. These are used for several reasons. They can be monitored to show if the tumbler is open or closed. They can be unlocked on their own, and Allen Bradley has placed a high safety rating on this device, meaning that its failure rate has been proven exceptionally low. Allen Bradley apparently made some sort of a statement stating that these cannot be read false either, basically saying that it's impossible for them to read locked with the tab outside of the device. So they were quite confused when this actually happened to us multiple times per day on that ride. For example, seat number 12 would read locked when we walk around to seat number 12. The seatbelt was all the way in the retracted position, not even close to the lock. And by the same token, seat number 7 would read unlocked when in fact the buckle was in and closed all the way. Vekoma SLCs use an electric actuator to lock and unlock the seats. These actuators are monitored by a limit switch in the fully closed position to know that the actuator has closed so the seat can lock. However, monitoring the seat actuator in the closed position does not mean that the restraint is closed. I can have a train fully empty, 100% closed, monitored, ready to go, and the seats are all in the open position where the restraint is wide open. And most roller coasters built before 1999 aren't even monitored at all. The ride only knows if the restraint release bar is in the up position or down position. Same issue though. If the restraint release bar is in the up position, the restraints are assumed unlocked. And if the restraint release bar is in the down position, they're assumed locked. In the end, the majority of rides these days can now tell when the restraint is down or up, but they can't determine if it's in fact actually locked. You still need the operator to verify that it's locked. So the next time your operator comes by to verify your restraint's locked, make sure you say thank you. That's going to do it for me for this episode. Make sure you like, subscribe, and share. That stuff really helps the channel grow, and I do appreciate it. I'm Ryan the Ride Mechanic, and as always, stay off the air gates. Bye.